All right, let's answer some questions. A viewer asks, is Newtonian physics laws that say energy can't be created or destroyed valid in the case of dark energy? So this is a really fascinating puzzle, and actually it even stumped Einstein. You see, when Einstein wrote his field equations and applied them to the universe, he got cosmological equations that showed that the metric was open. What does that mean? It means that the growth of space and time itself kept going. The Einstein field equations give us a set of rules for how the metric grows with time, and it showed that everything started out as a point. That's the start of the equation, and then as you give it time, it grows. So what Einstein did was he actually applied a cosmological constant that subtracted off growth from the metric and kept everything static so that the universe was steady state. And so we never had it growing or shrinking, it just stayed the same. However, when Edwin Hubble later looked at galaxies far away and found out that everything that we thought was the Milky Way galaxy, some of that was actually galaxies outside of the Milky Way, when he looked at the data, he found out that a ton of the galaxies were redshifted and were receding away from us. And the only way that could be possible is if space itself is expanding, and thus in every direction other objects that are far away are receding away from us. There's only a few nearby objects that are blue shifted or moving towards us. Andromeda Galaxy is one. But if you look statistically, if there was no growth and no expansion in the universe, there should be just as many objects that are moving towards us or blue shifted as away from us, and thus being red shifted. So the evidence from astrophysics that we found, what happened was cosmologists later went back and found out, hey, the universe actually is expanding. And so the original assertion that the Einstein field equations had, that energy wasn't conserved and that the only thing that we could say is that the metric is open and that energy can actually be growing and created with this dark energy, that is still alive today. Now, there's another question about this. What about at really short distance scales? Energy can also be violated for really short distances and really short amounts of time. So even locally, energy conservation is not always obeyed if the time that it happens is less than the uncertainty principle. So yes, classical physics and energy conservation is only valid at ordinary scales, but the real workings of the universe don't necessarily obey energy conservation all the time. When we think of dark matter, we think of something ghost-like, something hidden from us, something that we can't see, something that we can't interact with. But the truth is, the evidence for dark matter is there, but we have to look in the right places. Dark matter is all around us. The sun, every second it emits trillions of neutrinos, a form of dark matter that we cannot see and we rarely interact with. The average neutrino can travel through a light year of lead before it interacts with the nuclei of an atom. Its cross-section, or probability for interacting with a particle, is so tiny because it does not emit nor does it receive light. It does not interact with the electromagnetic field. It is completely and utterly devoid of an electromagnetic interaction. And yet, deep underground, they've been detected at many locations, including Fermilab. A new experiment, in fact, will detect them at a greater numbers than ever before. Currently under construction, and with a detector at both Fermilab and a FAR detector at the Sanford Underground Research Facility, also known as SURF, which is located in South Dakota. They will observe neutrinos produced at Fermilab. An intense beam of trillions of neutrinos from the production facility there will be sent over a distance of 1,300 kilometers with the goal of understanding the role of dark matter neutrinos in the universe. More than 1,000 collaborators are working on this project, and the experiment is designed for a 20-year period of data collection. They will investigate the strange occurrence of neutrino oscillations, a process known to occur with solar neutrinos produced in the sun, where the neutrinos can oscillate and change flavor. You see, there's 3 types of neutrinos: electrons, muons, and tauon neutrinos associated with their respective lepton particles. The electrons are the lowest mass and more stable form of the lepton, whereas the muons and tauons are higher mass, shorter lived, and higher generation of particles than the electrons. Electrons do not oscillate and change flavor into tauons or muons. Electrons stay electrons. Electrons can change into different energy levels, of course. However, they never change their identity. The fact that neutrinos do oscillate and change flavor, thus becoming a different type of particle, and that this oscillation is periodic and occurs as a quantum interference effect, where we have the 3 pure flavor states of electron, muon, and tauon neutrinos all combined into one superposition, and the interference between the different states produces the probability of detecting one of the 3 types. The fact that the neutrinos behave this way is a huge shock and was not predicted by the standard model of particle physics. Thus, we already have evidence confirming that the standard model is not enough to describe nature. The proof of neutrino oscillation was found in the early 2000s, yet we still do not understand how it works, even if we have the mathematical formulation that explains it. We don't understand exactly how to make the standard model better so that it incorporates neutrino oscillation and neutrino masses into the picture, because originally it was thought that neutrinos were massless. The standard model of particle physics also predicts them to be massless, but this is not the case. Thus, hot dark matter, also known as neutrinos, is our first major scientific problem that we need in order to fix the standard model and make a working model of nature and particle physics that incorporates everything and can explain everything. Therefore, this observational experiment is extremely important and will play a big role in the future of science. But what about cold dark matter? The dark matter out there in space that's supposedly helping form galaxies. What observational evidence do we have that it exists? The image you're looking at right here is from the Hubble Space Telescope, and it shows the distribution of dark matter, as in cold dark matter, in the center of a giant galaxy cluster named Abell 1689. This contains about 1,000 galaxies and trillions of stars. Hubble can't see the dark matter directly, but the astronomers have inferred its location by analyzing the effect of gravitational lensing, where light from galaxies behind Abell 1689 is distorted by the intervening dark matter within the cluster. The researchers have used the observed positions of 135 lensed images of 42 background galaxies to calculate the location and amount of dark matter in the cluster. They then superimposed a map of these inferred dark matter concentrations, tinted them blue on an image of the cluster taken by Hubble's advanced camera for surveys. If the cluster's gravity came only from the visible galaxies, the lensing distortions would be much weaker than they are. Thus, this map reveals that the densest concentration of dark matter is in the cluster's core. Abell 1689 resides 2.2 billion light years from Earth. This image was taken in June 2002 by the Hubble Space Telescope. In another piece of observational evidence that dark matter exists, we see a composite image showing the distribution of dark matter, galaxies, and hot gas in the core of a different merging galaxy cluster called Abell 520, which formed from a violent collision of massive galaxy clusters. The natural color image of the galaxies was taken with NASA's Hubble Space Telescope and with the Canada-France-Hawaii telescope in Hawaii. Superimposed on the image are false colored maps showing the concentration of starlight, hot gas, and dark matter in the cluster. Starlight from galaxies derived from the observations by the Canada-France-Hawaii telescope is colored orange. The green-tinted regions show hot gas as detected by NASA's Chandra X-ray Observatory. The gas is evidence that a collision took place. The blue-colored areas pinpoint the location of most of the mass in the cluster, which is dominated by dark matter. Dark matter is an invisible substance, yet we can see its gravitational influence here in this incredible image. Just because we haven't seen it directly with a telescope doesn't mean that we aren't looking for it directly. In fact, the Alpha Magnetic Spectrometer is a particle physics experiment module that is mounted on the International Space Station. It's recognized as a CERN experiment, and it's a detector that measures antimatter in cosmic rays. Cosmic rays are high-energy protons and atomic nuclei that move through space at nearly the speed of light. They originate from the sun and from outside of the solar system in our own galaxy and from distant galaxies. This information is needed to understand the formation of the universe and search for evidence of dark matter. The principal investigator of this experiment is particle physicist Samuel Ting, and the launch of the Space Shuttle Endeavour carrying this experiment took place on May 16, 2011, and the spectrometer was installed May 19, 2011. It's recorded over 60 billion cosmic ray events and 90 billion after 5 years of operation. Incredibly, it's observed over 400,000 positrons, which is a form of antimatter, essentially the antimatter version of the electron. Because cosmic rays are so energetic, it was thought that they could potentially interact in such a way that a dark matter particle, which is thought to be very high mass, could potentially be produced and detected by the detector. As of this moment, no dark matter particle has been detected. Thus, our understanding of dark matter is showing that it's still in its infancy. All right, let's answer some questions. A viewer asks, why do electrons exist as a probabilistic wave function, but protons and neutrons not? What accounts for this difference? Actually, everything exists as a probabilistic wave function, even you, but there's a reason we can't observe it in larger objects. Even it's harder to observe with protons and neutrons. The equation for the matter wave is behind me. Notice that the momentum is in the denominator. That means the more massive an object is, the smaller that wavelength is. We can actually use electrons as microscopes because we can diffract off of their matter waves. Their matter waves are so large, we can actually use them. However, more massive objects have much larger momentum. And remember, that thing in the top is Planck's constant. So it's really easy to shrink it down. And even our own bodies have a matter wave, but they're too small to observe. In my new book coming out shortly, I'm going to talk about a disagreement between the Einstein field equations pictured above and the Heisenberg uncertainty principle. While the Einstein field equations say that the gravitational force is due to a mass bending space and time at a precise location, the Heisenberg uncertainty principle says that the precise position and location of an object can never actually be known. There's always a quantum uncertainty due to the effect of the object behaving like a wave. But this is a problem for both theories because we have to know the precise location of an object to know its gravitational effect. For example, an electron would still have a gravitational force associated with it. But if its position is uncertain, that would mean that its bending of space and time is uncertain. So this is a major unresolved problem in physics. Without a doubt, the most dangerous forms of radiation are HCE ions. And these forms of radiation are the kinds that astronauts can experience in space. What makes these so dangerous is that they're incredibly fast moving, and they also have a lot of mass, so they carry a lot of momentum. But why do they have so much mass? Well, to start with, this form of radiation is not a photon. It's actually the nuclei of atoms. It includes the nuclei of atoms such as helium, carbon, oxygen, magnesium, silicon, iron, and even as high up as uranium. High-energy photons knock electrons away from neutral atoms and ionize them, leaving only the nuclei remaining. These nuclei are then charged and they're accelerated by magnetic fields and thrown towards Earth. There's an experiment that's been done with particles like photons or even electrons that's so insane you won't believe it. So there's this quantum mechanical property called spin, and it's a type of angular momentum. The classical version of it is the spinning of the Earth, because the Earth has angular momentum in terms of its orbit around the sun. That's orbital angular momentum, but it also has spin angular momentum. Well, in quantum mechanics, there's an analogous property, but it's different than in classical physics. You see, with this spin, it's like it always has a value, and it's either spin up or spin down when it interacts with a magnet, but nothing in between. It's completely different than classical physics where you have a continuum of values. It's either up or down, and this was demonstrated with an experiment called the Stern-Gerlach experiment. Okay, so let's say that we have two particles, like two photons, that have one is spin up and the other is spin down. But we don't know which one is spin up and which one is spin down. We can't treat it like as if the system, one of the particles has spin up and the other one has spin down the whole time. We have to treat it as a superposition where the particle doesn't have a specific value of spin until we measure it. That's right. It doesn't matter how far these particles travel away from each other. If they're in an entangled state, they do not have the specific property of up or down until we measure it. And they can be on other sides of the universe, through a wormhole, whatever you want. It doesn't matter. Until they're measured and a value is found, their value is indeterminate. As soon as the measurement is made, the other particle immediately takes on the other value. This property of superpositions and particles suddenly getting values is what Einstein called spooky action at a distance. Because in physics, any process is supposed to have causality, and it's supposed to have a length or duration of time in which to occur. And because these spin entangled systems collapsed and there was no duration of time, he said that couldn't be possible. That's spooky action at a distance. But it was later demonstrated in experiments to be the case after he had died. As recently as the 1980s, and even more recent than that, these spin experiments with collapsing wave functions and the particles being known happened. 841 million miles away from Earth and about 759 miles from Saturn lies the moon Titan. Titan is the second largest moon in our solar system. It's 80% more massive than our moon and 50% larger in diameter. But the most incredible thing about Titan is that it has this thick atmosphere. In fact, its atmosphere is mostly made out of nitrogen, which makes it very similar to the atmosphere on Earth. But there are many differences as well. The biggest difference is that Titan does not have any oxygen in its atmosphere. So the other difference is that it contains a larger amount of other components like ammonia, and it has a weather cycle because of this atmosphere and also because of its components. And as a result, it rains and it has liquid hydrocarbon lakes on the surface that were revealed when the Cassini space probe looked at Titan in more depth. It has orange skies, so if you were on the surface, you would see this thick orange haze. It's difficult to say what the visibility would be on the surface because we don't have very clear pictures of the surface, but there is some limited concept and pictures of the surface at this very moment, and there will be more in the coming future for sure. The other thing that's very fascinating about Titan is that it's actually proof that a moon could sustain life, because there was a debate about the size that an object would need to be in order to hold on to gases. And we pretty much know what the limit is for size in order for something to have an atmosphere, but Titan shows us that a size does not have to be nearly the size of the Earth in order to have a sustainable atmosphere. So that's an incredible result. Now, it is true that because of its size, it has very fewer components like hydrogen and other things like that, because they just escape. It doesn't have the gravity to hold on to those kinds of gases. But Earth is also similar to that. That's why we don't have helium and hydrogen in our atmosphere on Earth, because of the size. It just escapes. Are X-rays safe? Is it safe to go to the dentist and get an X-ray for your mouth? Is it safe to go to the doctor and get a CAT scan? Well, the thing about it is that yes, it's safe, but I want to explain why it's safe and why it's not safe to get a lot of X-rays, because it's a little bit more complicated than you might think. So first and foremost, Einstein figured out that to ionize something, to knock an electron off of an atom, it's not the intensity of the radiation that matters, it's the frequency. So what happens is it takes a single photon of light to ionize an atom and knock the electron off of it. That's also how DNA is damaged. So that's why it's relevant to the topic of X-rays. So what you're thinking is, wait a second, when I get an X-ray, those X-rays are strong enough to knock electrons off of my cells, right? Because they're strong enough to penetrate through. Are they strong enough to do damage? And the answer is maybe. They might be strong enough under the right circumstances to ionize your cell, an electron in your cell. But here's the thing. They've dialed it in, the radiation levels, that is, on these machines, so that they really don't use that many photons. They use a very low intensity of, somewhat high frequency X-rays to do the imaging. But the thing is that our bodies have evolved to repair damage done by this kind of radiation, because we get that kind of radiation from natural sources too. We get it from the sun, and we get it from soil. The ground gives off radiation, and every human gets exposure to it. But the thing is our bodies can repair very minor damage to our cellular DNA, with the exception of a few people. There are some people where for some reason, that mechanism is hindered and they're very much at risk for cancer. And if they have those genetic conditions, they're not advised to get an X-ray. Another example is somebody who's pregnant, because if the fetus is developing, the cells are dividing particularly rapidly and they're very vulnerable to radiation. They can't protect themselves like a normal adult or even a child's cells will be able to repair the kind of minor damage you get from an X-ray. But the whole point is that these machines are incredibly safe because they use a low intensity, and even if there is a little tiny bit of damage, your body will repair it. What is lambda CDM? If you read about cosmology, you'll see this term lambda CDM pop up. What it means is, it means a universe where we have dark energy and dark matter. The dark energy is represented by the lambda term. That's because when we have the Einstein field equations, we have a lambda in front of that term that gives the expansion for the metric, and essentially the dark energy is associated with that term. The CDM just stands for cold dark matter. The fact that we think that the majority of the dark matter in the universe is low velocity so that it's not moving relativistic speeds, so it clumps at a certain point and causes galaxies to form and serves as the main gravitational potential. If you want to learn more, check out my latest documentary on YouTube. There's a link in my bio. Thanks a lot for watching and have a great one. All right, enjoy this latest clip from my brand new documentary on dark matter out now on YouTube. Click the link in my bio and watch the full thing. It's an hour long. I promise you will love it. Now, interestingly enough, there's actually a lot that we can learn by how big galaxies are. Because if the dark matter particles that form the majority of our universe and our galaxies were fast moving, like, say, neutrinos, which are dark matter that travel almost at the speed of light, well, then we wouldn't have all of these types of gravitationally bound structures forming, because the dark matter would have too much kinetic energy to be gravitationally attracted to any meaningful size. So the fact that we have these large structures and these galaxies forming even in an early time in the universe points to an identity for a dark matter particle that is massive and also slow moving, hence the term cold dark matter, as opposed to hot dark matter, which would be a fast moving form of dark matter, like a neutrino. Hey everybody, don't forget to check out my new YouTube channel. I've got an hour-long documentary on there. I promise you will love it. The link is in my bio. Instagram won't let me put a clickable link in my posts, unfortunately. So just go right up to my bio on Instagram, click on the YouTube, and if you like what you see, click and subscribe. It really helps out. Thanks again for all your love and support. Peace. All right, let's answer some questions. A viewer asks, why do electrons exist as a probabilistic wave function, but protons and neutrons not? What accounts for this difference? Actually, everything exists as a probabilistic wave function, even you, but there's a reason we can't observe it in larger objects. Even it's harder to observe with protons and neutrons. The equation for the matter wave is behind me. Notice that the momentum is in the denominator. That means the more massive an object is, the smaller that wavelength is. We can actually use electrons as microscopes because we can diffract off of their matter waves. Their matter waves are so large, we can actually use them. However, more massive objects have much larger momentum. And remember, that thing in the top is Planck's constant. So it's really easy to shrink it down. And even our own bodies have a matter wave, but they're too small to observe. What is this crazy photo? This is a picture of an astronaut doing a spacewalk and making a repair to the alpha magnetic spectrometer. This instrument measures antimatter, specifically positrons originating from energetic events such as cosmic rays coming in. What's fascinating is there's no preferred direction to the positrons that are being detected, which could indicate that dark matter is actually responsible for some of the positrons. While it's still a work in progress, the background radiation of positrons coming in shows that there's no preferred direction, meaning it could be originating from dark matter and anti-dark matter in the galaxy halo of dark matter, and that produces the positrons. That's one possibility. A brand new documentary on YouTube about observational detection of dark matter. Check it out. All right, let's answer some questions. A viewer asks, is dark energy consistent with Newtonian physics laws that say that energy can't be created or destroyed? This is a really interesting question. It turns out that the first person who discovered dark matter accidentally was Einstein when he wrote down the field equations for the universe. But the term that had dark energy in it, he thought was just mathematical and not actually physical. So he added a term, a lambda term, to balance it out and make it so that the universe was static and didn't expand. But when they later discovered that most of the universe is redshifted and expanding away from us, they went back to those equations and found out that the dark energy does exist and it doesn't conserve traditional energy conservation theorems like we have in classical physics. It's incredible, but it's true. And actually, at really short scales, energy conservation can also be violated in quantum field theory. All right, let's answer a question. A viewer asks, in regards to dark energy, everything is growing. Does that mean particles are getting larger or their existence skipping across diverging space-time quanta, or neither? Well, dark energy is the energy that goes into causing new expansion of space and time. And as far as we know, that may not obey energy conservation. The photons and other particles do obey energy conservation relations. Photons, for example, from the early universe that form the cosmic microwave background radiation are stretched out with the expansion of space and redshifted. So to answer your question, these particles are affected by the expansion of the universe, but they're not given more energy. It's just that the overall volume in which they exist is expanded and increased. So they respond to the dark energy, but not in a way that gives them more energy. All right, everybody, gather around for the amazing, tragic story of Vulcan, the planet that was not meant to be. In the early 1900s and 1800s, scientists thought that there was a planet nicknamed Vulcan that was inside the orbit of Mercury, even closer to the sun than Mercury. Why did they think this? Well, Mercury went on an orbit that was not closed. It experienced perihelion, which means that after it completed 1 year, it wasn't in exactly the same space. Here you can see two hypothetical orbits of Mercury in blue and green shown going around the sun, and Vulcan in that inner orbit. Vulcan was supposed to be the reason why Mercury was experiencing this perihelion. It was thought that Vulcan was disturbing its orbit. They had reason to suspect this because this was actually what was going on with Pluto and Neptune. However, it turned out that this effect was actually caused by general relativity. Without a doubt, the most dangerous forms of radiation are HCE ions. And these forms of radiation are the kinds that astronauts can experience in space. What makes these so dangerous is that they're incredibly fast moving, and they also have a lot of mass, so they carry a lot of momentum. But why do they have so much mass? Well, to start with, this form of radiation is not a photon. It's actually the nuclei of atoms. It includes the nuclei of atoms such as helium, carbon, oxygen, magnesium, silicon, iron, and even as high up as uranium. High energy photons knock electrons away from neutral atoms and ionize them, leaving only the nuclei remaining. These nuclei are then charged and they're accelerated by magnetic fields and thrown towards Earth. What level of radiation exposure can an astronaut expect to experience while in space? During a 6-month mission, an astronaut can expect to receive anywhere from 50 to 2,000 millisieverts of radiation exposure. For comparison, the biological damage to the human body has been documented starting at around 100 millisieverts. So you can see where the upper range of 2,000 millisieverts of radiation exposure is a bit of a concern. Of particular risk is when astronauts go on these types of spacewalks pictured here, where they're actually openly exposed to the atmospheric radiation from cosmic rays bouncing off of Earth's atmosphere and also directly from the solar wind from the sun. Luckily, NASA has been conducting research to make spacesuits much safer for future missions. Investigations are currently being made to make more protective materials for future missions. Why were early stars so much more massive on average than stars are today? Well, the answer has to do with quantum mechanics. You see, in the early universe, only hydrogen and helium were available for these stars to form. However, hydrogen and helium have only 1 or 2 electrons respectively, and this means they have fewer energy levels. And so there's not as many ways for these gases to radiate away their energy. And radiating away their energy is critical because stars can't form unless a gas cloud can radiate away its energy and get cold and gravitationally collapse under its own mass. So the early stars had to be much more massive because they had a lot more radiation pressure because the hydrogen and helium from which they were forming was just hotter overall. So these stars were maybe 100 times larger than our sun is today. Why were massive early stars so much bluer than our own sun? The answer lies in these curves here. You see, at a higher temperature, the peak wavelength shifts to a smaller value. Blue wavelength light is shorter than red, for example, or orange. And so these massive blue stars in the early universe were much hotter than our sun. This is Wien's law. This is the equation that explains what the peak wavelength of the light is. That's lambda max. That's essentially the color that the star will be because it peaks at that wavelength. B is just a constant of proportionality that's measured experimentally, and T is the absolute temperature. You can actually use this formula to figure out what your peak wavelength is. Pretty cool. And you'll see that it's in the infrared range of radiation. In the early universe, when stars first formed, they were much more massive than they are today on average. This is an image I created of 3 early stars. Here you can see that they're a bright blue color. The reason for that is because these stars are much hotter than our own sun is, and they emit at a peak wavelength that's much smaller and more blue. This is true for any star. The hotter the star, the more its wavelengths will be shifted to a bluer range. Now, the reason these stars got so massive is because in the early universe, we only had 2 elements, hydrogen and helium. So these stars started out being made out of exclusively just these elements. These elements are much harder to cool off than if they have heavier elements in them as well. The end result is that more mass was required in order to overcome the thermal pressure and form into a star. What are the Einstein field equations really? They're really directions for a map of 4-dimensional space. Just like you can have a map of the Earth that maps out the continents and where they're located in relation to each other, you can also make a map of the 4-dimensional universe. What's interesting is that mathematically, this is achievable with 3 spatial dimensions and 1 dimension of time. But you do need that time dimension because, as we've talked about before, time depends upon various properties of space, and it changes in relation to those and in relation to the influence of energy in different locations. Here's the Einstein field equations in all their glory. Now, this equation is incredibly general. As you'll see, there's these funny symbols mu and nu, the thing that looks like a U almost in a V. Those are subscript indices, and what those denote is the dimensionality of the object called a tensor. You see, a scalar is something that just has a magnitude. It's a rank 0 tensor. A vector has a magnitude and a direction. It's a vector. A tensor is anything that's those or higher dimensionality, like 2 or 3 different directions. And these things can become infinite. It just depends. With Einstein's field equations, it's apparent that we can actually achieve the relations with mostly rank 2 tensors. Now, what this actually describes is how flat space is related to the curved space. In other words, if we have gravity, the flat space and the curved space disagree with each other. Basically, we need a way that we can describe all the relations of the vectors so that they stay consistent. And to do that, we need the tensors that relate the curvature from one component to the next, because they'll change as we go from place to place. We do that with the Riemann curvature tensor, and then we can contract that and make the Ricci tensor, and ultimately produce the Einstein tensor, which makes the Einstein field equations. The details are kind of mathematical, but the important thing to keep in mind is this is a map in 4 dimensions, and if there's a break or a discontinuity in the map, that produces a black hole or a wormhole. And these discontinuities are singularities, or places that are disconnected from the rest of the map. So we have asteroids, and the question is, how often do they strike the Earth, and what is the risk? So it turns out that asteroids do strike the Earth pretty often, but most of them are pretty small, and when we talk about an Earth strike, we should really be more precise and say they explode in the air generally, because the atmosphere causes them to break up and explode before they ever even touch the ground. However, fragments can then later land onto the Earth, and they are often discovered. However, there was an event in June 30th, 1908, where an asteroid flattened 80 million trees and basically completely demolished 830 square miles. For perspective, if that had hit Los Angeles directly, it would have completely destroyed it. The asteroid was about 200 feet in size, and it actually broke up in the atmosphere and exploded, so it never actually struck the ground either, but it did a ton of damage.